Welcome back. In part two of the section 5.1 lesson, we're going to take a look at two samples of using integration to solve equations. And the first type is called a differential equation. Differential equation is really nothing more than an equation that has a derivative as part of it. For example, whether this is y prime, f prime of x, here it says dy dx equals 3x squared minus 1. Now, when we find the integral, we know it's not going to be unique. What that means visually or graphically is we end up with an answer that's a bunch of parallel curves. So, for example, when I find this integral, it's going to be a cubic equation. And we know the look of all cubic equations. So if we think of a whole bunch of these cubic equations that are pretty much similar, the same kind of graph, but shifted up or down, that's what we have with that plus c. We want to find the specific one that goes through the point 2,4. So let's look at that example and hopefully that'll make more sense. To solve this differential equation, we know that y is going to simply be the integral of 3x squared minus 1 dx. You notice I didn't really have to go through the process of putting the dx over here, integrating both sides, because we know we're going to integrate the function. Therefore, y is going to be x cubed. We've seen that already. The antiderivative or integral of 1 is x, because I'm using the variable x. Then again, we have that plus c. This sometimes is referred to as a general solution to a differential equation. So if it's a general solution, and that's all I wanted, I'd be done. However, we want to find what we could call the particular solution, meaning I know a point that it passes through. And hopefully you're guessing that all that means is we're just going to put a 2 where the x is and a 4 where the y is. So a 2 here and here, a 4 for the y, and solve for c. So we get 4 equals 8 minus 2 plus c. C, therefore, is going to be, that's 6, I believe negative 2. So now we have our particular solution of x cubed minus x minus 2. And again, that is called a particular solution. The general solution, again, a family of parallel cubic curves. They all pretty much look the same. But the particular solution is the one of all of those curves that happens to go through the point 2,4. Now this can be used for any type of function. As long as you can get the integral, you can pinpoint what that c is. Now another thing we can do with this integration is kind of return to some physics. Up to this point, we already know that if we have a position function in terms of time, we can find the derivative to get the velocity. We can then find the velocity at certain time periods. We can then find the derivative again to get the acceleration, and then find the acceleration at certain time periods. Many of our problems were kind of free fall problems, meaning an object just going up and down, away from the Earth and down towards the Earth. We also had a variety of problems that were kind of linear problems, going back and forth along a line. So it wasn't relying upon the acceleration due to gravity. Here is an example that shows us how we can use integration to answer a question about the position of the function when we don't really know the position function. The situation is we have a ball that is thrown upward at 64 feet per second from an initial height of 80 feet. Now, one thing that we would always be told is what the gravity is, and on Earth, in terms of feet per second, the acceleration would be negative 32. So to do part A, I'm going to start with my acceleration function. And I know that's negative 32. I don't need the units. I can take care of those later. Now, if I want to find the integral of acceleration, hopefully you realize it would be velocity. So the velocity function is going to be the antiderivative of negative 32. Now, I'm not going to use an x, because the variable is going to be t, because everything is with respect to time. And here we have negative 32t plus some constant. Now, I can use something in this problem to figure out what that constant is. And what I know is that this is my initial velocity, because the second it leaves my hand, it's going 64 feet per second upward. So I know that the velocity at time 0 is 64. If that's true, that means you should be able to put a 0 in for t, and then get the c to be 64. Many times, that c is just going to be your initial velocity. Quite often, we even call this v sub 0, but I don't want to get into that right now. So what I have is the velocity equation is negative 32t plus 64. If we then go another step and we want to integrate this function, where the antiderivative of velocity should be position. Remember, we tended to use an s for position. The antiderivative of negative 32t is negative 16t squared. I basically either just knew that or I used the power rule. Add 1 to the exponent, divide by the new exponent. The integral of 64 is 64t. And then guess what? There's another constant. Now, they're not the same constants, so maybe we could use subscripts. We don't have to, as long as we realize they could be different. Now we go back to the problem and ask ourselves, what is the position at time 0? Well, at time 0, this thing was already 80 feet high, so that's 80. So now I solve an equation. I let 80, which is the s of 0, be negative 16t squared. The t is 0, plus 64 times 0, plus c2. So guess what c2 is? It's that initial height, which is going to be 80. So it seems like a lot of work to get to that point. Anyone who's taken a little bit of physics would maybe have just known this is true. I think we've even looked at some problems ourselves where we kind of realized that this coefficient is the initial velocity and this value is the initial position. So that's part A. Now for part B, when does the ball hit the ground, which is really our ultimate goal in this problem, we just have to set this equal to 0. So for part B, we are going to let that position equal 0. You can factor out a negative 16. You get the factors of t minus 5 and t plus 1. We could say t is either 5 or negative 1. I don't really want negative time, so it's going to hit the ground in 5 seconds. Now, this whole idea of solving differential equations is something that a few of you may continue to work on as you take more calculus courses. Eventually, there could even be a full course on differential equations. The reason they tend to be so important in the sciences and even mathematics, of course, is that things change. So if we describe a rate of change of something, we then we can find the value of that thing by solving the differential equations and, of course, using integration. For any of you that might be Simpsons fans, there's the TV show, the cartoon. There was a Simpsons episode where Bart fell out of his treehouse, and it took him 5 seconds to hit the ground. And just from that information, you can find out how high the treehouse is. Again, using this same type of acceleration. Since he fell from the treehouse, his initial velocity was 0 because he wasn't moving at the time, and his initial height is what you want to find. That's a little bit different in getting that height, but it would be kind of neat to see if you could come up with that answer. Just as a hint, it's rather high. And the big question is, were you surprised he only broke his arm? Hopefully we can get into that sometime. If you have questions, let me know. But that basically wraps up Section 5.1 topics and examples. Your first priority is to get the one worksheet from Chapter 4 to me as soon as you can. Second priority is start making progress from section 5.1. 2 days from now, if you look at the calendar, I will have another video, and we'll pretty much stay on that every other day pattern for a while until we pause for quizzes, worksheets, and tests. So once again, I hope everyone is fine, and enjoy your day.